So for instance, if I wanted to solve this particular problem, this problem number 3, we see that this is a steady flow problem with refrigerant 134A entering a isentropic compressor. It's coming in at 25 degrees Fahrenheit as a saturated vapor, which means that it's all the way at the right side of the dome with a quality equal to 100% or quality equal to 1. And then it finally exits at a pressure, and again, it's exiting at that particular pressure after going through an isentropic compression event. If we assume that the compressor operates at steady state and there's no significant heat transfer with the surroundings, then we should be able to solve the problem. Kinetic and potential energy effects will be ignored. And so the first thing we're going to do is we're going to look at the isentropic process, going from 25 degrees Fahrenheit as a saturated vapor, expanding isentropically to a pressure of 100 psi. And so I'm going to now go back. I'm going to go to my test. Under test, then I check my applications. The application is an open system. It is a single flow open system as a compressor. The substance is a phase change substance. In this case, it's R134A. I then can go into the application. I need to address the fact that the substance in question is not water, which it defaults to, but R134A. I now can generate state 1. What we know about state 1 is that the temperature as given in the problem was 25 degrees Fahrenheit. And it was also a quality equal to 1. And so under that particular scenario, we see that the pressure is 254. Now what I'm going to do here is I'm going to go back and I'm going to restart the application. But this time I'm going to start from scratch as in English. And so once I did that, you'll see that all of the units here default to the English unit. Okay, again, R134A. Have to be a little bit careful here. If you stretch out your program here, you'll see that this is degrees Fahrenheit, and so it's 25 degrees Fahrenheit with a quality fraction equal to 1, and we see then that the refrigerant comes in at a pressure of 36.9 psi. Okay. So we have the incoming condition. We didn't know, there wasn't any mass flow determined or specified for this particular problem. And so we're going to just put in 1 pound per second, just as a reference point. And so we now need to have it go through the isentropic process. 34A. What we know in this particular case is we do know the final pressure. The final pressure was 100 psi. Because we know that it was an isentropic process, the specific that is coming out is equal to the specific entropy going in. And so with that in mind, and with this particular pressure, we have the two known thermodynamic states, and so our output state is fully defined, and we see that our outgoing temperature in degrees Fahrenheit is 85.33 for the isentropic compression in this particular case. I'm going to go ahead and I'm going to say that since this is a steady state process, that the m dot is just equal to the incoming MDOT. So for this particular problem, we have now solved the problem. If I were to go back, the first thing that was asked is to sketch the TS diagram and determine the exit temperature. Again, this is for the isentropic compression process. It also then is asking for the isentropic work required to do that. Now you'll see the work that they're asking for is BTU per pound mass. And so they don't really care how many pounds are going through. They're looking for the specific work on a per pound basis. And so in this particular problem, since we specified that the MDOT was 1 pound per second, when we then look at what happens to the enthalpy, which is related directly to the work, the change in the enthalpy, which will be in BTU per pound, if I then multiply that by the MDOT, I then would have the BTU per second. That would be the rate of work that's generated. Now, in our particular case, all we're really interested in, because of the fact that we're looking for the specific work, the BTU per pound, through the compressor in an isentropic case, we are just looking for H1 and how H1 changes to H2, and the difference between the two enthalpies levels is then equal to the specific work. Again, this is only the case when we neglect any kinetic or potential energy differences. And so if we wanted to see what this looks like on the graphics panel, we can go to the graphics panel for the TS plot, and we see that state 1 is identified. You see it as at a given temperature. We see that it's located right on the dome line, the saturated vapor condition, and then the isentropic process, which is straight up. Let me go and I'll look at the entropy is the x-axis, and so an isentropic process then is just going straight up from that particular point, remaining in the superheated region. And so the answer to this first problem then is simply, there's the sketch, and the exit temperature is the temperature that we found for state 2 after the isentropic compression, and that temperature was specified on the output screen. The isentropic work is just the difference between the H2 minus H1. And then the last part is to determine what happens if we allow it not to be isentropic, but rather non-isentropic, have some reversibility, some irreversibility occurring, and then determining what the actual compressor efficiency is. And so in this case here, we're allowing the temperature to rise because of irreversibility up to 120 Fahrenheit. And we're then going to determine the isentropic compressor efficiency and look at where that new location would be on. So again, we go back to our software, and if we wanted to determine what the work was in that first isentropic step, we could go to the device panel. We could set up the incoming state was state 1. We could say the outgoing state was state 2. We could say that there was no heat transfer, and we would find that the work on a rate basis would be equal to this. Negative implies that it's work going into the compressor. Unfortunately, the software doesn't have a unit here corresponding to BTU per second, which we would recognize since we're running 1 pound mass per second through. This would correspond to the amount of energy per pound mass. And so this number in foot-pounds per second, if we divided this by 778, which is uh, the relationship between BTU and foot-pounds, we would then have the value that we were looking for. And so I'm going to go ahead, go back to the state panel, and what we want to do then is we want to identify or generate a third state, which is the actual state coming out of the compressor. And so what we know about that is it's no longer isentropic, but we do know what the temperature is. And the temperature, as we saw back here, the temperature was 120. And so we're going to put in 120 Fahrenheit there. And then the question is, what else do we know for that final state? Well, we go back and we see that if this is the actual temperature, we make the assumption that it exits at 100 psi at this higher temperature. Okay, and so we go back and we know that the pressure is actually equal to the pressure that we had specified at state 2, which corresponded to the 100 psi. So now we have our two thermodynamic states. While we're at it, we can go ahead and say that this is m dot, this is equal to m dot 1, which is also equal to m dot 2. And all of the thermodynamic properties then are determined. The one that we're the most interested in then is the elevated enthalpy associated with that third state. And we would compare that to the enthalpy of the isentropic compression of 115. And we compare both of those to the enthalpy of the incoming fluid. And so we have our three states. If we wanted to see what those three states look like on the graphics panel, here straight up is from 1 to 2, we see is the isentropic process. And then the actual compression would be from 1 to 3. If I wanted to add some constant pressure line, you can then see that there would be a constant pressure line that would go through from 2 to 3. Okay. And if I had said I want a constant pressure line to go through 2 and 3, I could have said through state 2. So that is the constant pressure line corresponding to 100 psi. And so with that in mind, now we can go to the I/O panel, do a super calculate, and when we do the super calculate, they then see that here is the input that was put in for state 1, state 2, and state 3, and then the output is also presented to us, and basically we see here's the enthalpy coming in, here is the enthalpy going out if it's isentropic, and then finally here is the enthalpy H of the real case when the entropy actually did increase due to irreversibility as it went from 100, as it went from the original condition to 100 psi at 120 Fahrenheit. Okay, so one of the nice things about the software is that you can, in the input, you can have it you can have it do some calculations. One thing you can do is you can say, well, I want to highlight what H1 is. All you have to do is type in equals H1, and you'll see that it gives you the value of enthalpy 1. If I also said, let's highlight enthalpy 2, it gives you the value of enthalpy 2. If I wanted to highlight the value of enthalpy 3, you see that that's the value of enthalpy 3. Okay, now one of the things you need to be careful with is the enthalpies are different because the I/O panel does everything in SI and not in in English. And so if I went back to the state panel, I could, if I wanted to, switch this over to kilojoules per kilogram, and I get the 286. If I went back to state 2, switching it over to kilojoules per kilogram, I get the H2. And then finally, I can do the same thing here, and I get the 247. So again, going back to the I/O panel always works in SI units. So those are our three enthalpies, and all we really want to do now is we can calculate the isentropic compressor efficiency. And what that actually is going to be is the isentropic work. And I'm going to just go ahead and say work isentropic. And we know that that work is the outgoing enthalpy minus the incoming enthalpy. So we see that the difference between those enthalpies is 20.6. And as you see here, because I said output minus input, we see that it's a positive number, and a positive number means that we had, in this particular case, we raised the enthalpy because this compressor is got work that's going into it, which a little bit different than work being generated by the system. And so if I wanted then to look at the actual work, I know that the actual work would be H3 minus H1, and I see that the actual work is 39.94. It takes more work for the fluid to be compressed because of irreversibilities. It's coming out at a higher temperature because of that, and now we actually have the actual work that is required. So the isentropic efficiency, let's just call it eta, is related to the minimum work divided by the actual work. And so that would simply just be the W isentropic divided by the W actual. So we see it's going to be 20.6 divided by 39.9. Oops, actual. And we then see that it's about 51%. So 51.7% is the isentropic efficiency associated with this particular process. And so again, we look back and we see, okay, in case C, we wanted to figure out what the isentropic compressor efficiency is. And again, the efficiency is always a number less than 1. And in this case, because it's a compressor, it's going to be the minimum work divided by the actual work, which is going to be higher. And so we calculated the two works, and then we were able to determine the efficiency. And so had this been a homework problem, we would have then gone in, done another super calculate. And when you do a super calculate, you see the user code blocks showing up here and all the information showing up, as well as the calculations that were made in determining the three states and the enthalpies associated with those three states, keeping in mind that the enthalpies are in SI units, and they are specific enthalpies associated with this particular system. Had gone back to the device panel, I only generated the device panel for the isentropic condition. I could, if I wanted to, I could set up another device, and have that device being the compression, the actual compression going from state 1 to state 2. Again, no heat transfer. And in this particular case, I would then have the value, a higher value of work, and it would be this work that I would then divide this work by this work to get that isentropic efficiency. And in this particular case, you see that the enthalpy, because I specified it was a compression device, we see that it's a negative number, which implies that heat is going into the system, or I'm sorry, work is being done on the fluid into the system. Okay, so that's all for this particular problem. I'm going to go ahead and shut down, stop the recording.